Okay, good morning everybody. So to recap Tuesday's lecture, we covered a different type of sensor, capacitive sensor. The main use of capacitive sensors is either very fine measurements like down to 1 atom movement, or a capacitive sensor is a standard sensor used in micro machining or integrated sensors where you want to have a silicon chip and you want to integrate some sensing into the silicon chip, for example accelerometer, pressure gauges, distance or weight. So all these devices work best with the capacitive sensor, which is integrated into a silicon chip, because it's very easy to make a capacitor monolithically on a silicon wafer. It's much more difficult to make an inductor. And because if you integrate things in a silicon chip, the preamp or the amplifier can be placed next to the sensor, and then you can run at very high frequency. Because if you want to make a normal system with an LVDT which runs at high frequency, you have problems with the coil, you have problems with the wiring. In general, the smaller the dimension, the easier it is to make things operate at higher frequency. Can somebody guess why that is? Why is the smaller the dimension, the easier it is to make things operate at high frequency?
Inertia.
Pardon? Inertia of mechanical and good, and also there's an electrical reason. Yes?
Parasitic.
Yeah, parasitic capacitor and inductance too. When you have connecting wires, they have inductance. So when you shrink things down, there is less inertia, less parasitic capacitance, less inductance. You can run them at very high frequencies. So because of this, the fact that a capacitive sensor can be integrated into the silicon wafer and with the amplifier means the whole thing can run at very high frequencies, which compensates for the fact that the actual capacitors are very, very small. And I also mentioned to you a good rule to remember Tuesday, that you are trying to design electrical circuits that the impedance you are working with is not very high. So you don't, if possible, you're trying to avoid circuits where the impedance is many megohms. Because then if you have some dirt and it causes a leakage pass, it affects the results. So again, if you have a sensor, and the sensor doesn't just have to be a capacitor, any kind of sensor, it could be a thermocouple, could be a chemical sensor. There is always a chance that there is some leakage path formed. Okay, and you want the Z of the sensor, you want the Z of the sensor to be much lower than the leakage path. So this current will not affect accuracy much, where this is the main current. So if you're dealing with capacitive sensors, which are typically picofarad range, you want to run at a very high frequency, because the Z is 1 over 2 pi Fc. So if C is very small, you can make F very high in order to bring Z to the range, which is a magic range of kiloohms, maybe 100 kiloohm, but not megohms. Now, some sensors you don't have a choice. Some sensors have to operate at megohms and even gigaohms, like electrometers. There are some sensors which actually operate at many gigaohms, but those sensors have great caution taken and special design rules that the sensor can operate at such high impedance. But if you have a choice, you're trying to bring everything down to fairly low impedance, so you're not very sensitive to leakage. For example, if you are working at megohms and if you just touch the wires, already your body is 100 kiloohm, it will affect the results. Or any kind of little problem, especially dirt and moisture, will affect the results. So in a capacitive sensor, when it's integrated in the chip, C is very small, okay? C is in the order of 1 picofarad or less, sometimes it's even 1 nanofarad. So this is an actual sensor like the one I showed you Tuesday, and this can be as small as 1 femtofarad when this is inside the chip, when this is inside the silicon chip, but you compensate by making F, say 1 megahertz or even 1 gigahertz. So altogether the Z works out in the right range. And I showed you that even if the sensor is single-ended, like a capacitive sensor, you can make a differential by doing some tricks, making a symmetric sensor and so on. Now this differential thing, there is two ideas which are not the same. One idea is a truly differential sensor like LVDT, or what I showed you is a capacitive sensor. Another idea is what's called a dummy sensor. Sometimes you cannot make the thing truly differential. For example, if you have a strain gauge, you cannot make it truly differential, but you can make it, and if you recall, I drew a strain gauge bridge a couple of lectures ago. So this is ground, this is plus V, you put a detector here, and this is the one which is changing when you, so all these are R, and this is X. To make it simple, I made all the resistors the same. So when this is stretching, the resistance changes and you get a voltage. I gave this as an example of a null sensor. Now this is not a truly differential sensor. A truly differential sensor would be if this gets bigger, this gets smaller, and then you get the difference. That would be much better. Like you could make a truly differential strain gauge in some occasions. For example, when you have a cantilever bending. When you have a cantilever bending, this side stretches, this side compresses, so you can actually put two strain gauges, one on top and one on the bottom. This is a neutral axis, and then the strain gauge will be truly differential. That will be very good. Now the reason we want a differential is to compensate for non-measured variables like temperature. Right? If the thing gets warm, the resistance will also change. But if you make it truly differential like this, the temperature will cancel out. All what you get is the real effect of the stress or strain. Now, but this, most applications, a strain gauge is applied to one side of a surface, and it's not truly differential. But what you do, you put a dummy sensor. You put a sensor which is constructed the same way as this one, and you stick it next to this one, and the dummy sensor doesn't stretch, so it's not truly differential, but it's still subject to the same temperature, same humidity, same electrochemical action. So there is a fine point here. You can make a truly differential sensor, which is the best. If you can't make a truly differential sensor, at least you should make it in some symmetric configuration and put in a dummy sensor. And this dummy sensor will mimic all the changes which happen to the real sensor except for the measured variable, like strain. Okay? So if those of you who looked at the picture, what a strain gauge actually looks like, a strain gauge actually looks like this. If this is a strain you want to measure, the strain gauge looks like this. It's usually laid out as a sticker, a very thin, flexible label that you can stuck to the metal and stretch with it. And it has one winding like this. That's done by etching, very much like a printed circuit board. And this is X. This is X because if this stretches, these wires will stretch. Okay? And then it has another winding like this. Again, this is etched. Okay? And this would be R. This would be X, and this would be X, and this would be R. And the idea is if you stretch it this way, these wires will not stretch. Because that's like a spring. The wires can just open up without stretching. These wires have to stretch. Okay? So if there is a temperature change, this and this will be affected the same. If there is a corrosion, aging, dirt, these two will be affected the same. But if you stretch it, one will be affected, one not. Okay? So I just want to make sure you understand the fine point between a truly differential sensor, where one side gets bigger, the other side gets smaller, or between a sensor which looks like to mimic a differential configuration by putting a dummy sensor on the other side. It's not as good as truly differential, but in a lot of ways it does the same. Say this noise reduction, if noise is radiated to both sides, the dummy will pick up the noise. So you still get some noise cancellation. You'll get many of the benefits of differential. You wouldn't get the doubling of the signal. And there is something else interesting about a truly differential sensor, which is not so obvious. If each side is not so linear, by making it differential, you improve the linearity. I didn't get into that when we talked about differential sensors, but if you do the math, if you take an LVDT, for example, and instead of getting a straight line per side, you get some distorted line, which happens a lot in sensors because of imperfections construction. It turns out if you do the difference, some of the distortion components will cancel out. And that, I don't want to go into that, it's not very important, but it's easy to see, because usually a nonlinearity in a graph can be represented by y equals ax, which is a linear part, what you want, plus bx squared plus cx cubed, and that's usually enough. That's 3 terms of representing nonlinearity. Now let's say that you make a differential sensor. So you have something which looks like this. It's, instead of being linear, it's represented by this cubic equation. Now let's say that you put this against the dummy sensor, nothing would change. Okay? You'll still get this minus some fixed amount, but the nonlinearity will stay, because the dummy sensor is not changing. It's just to compensate for long-term drift. But when you stretch it, say here, the dummy sensor is not changing. But let's say you can make it differential. Let's say that this was also a sensor, like in the case of the beam, that one goes up, one goes down. Okay? So one side is here, the other side is here. So y1 will be this. Now y2, which is the second sensor in a truly differential system, it will be the same, but x will become minus x, because it goes in the other side, right? So the x, the signal is reversed. You're taking the difference, okay? So now, if x becomes minus x, this will be minus ax. This will stay plus bx squared, because x is squared. This will be minus cx cubed. Now, in a truly differential sensor, you're taking y1 minus y2. If you're taking y1 minus y2, you'll get 2ax, which we already know. A differential sensor doubles the signal, so that we expected. Now, but then these two will cancel out, and you get here a plus 2cx cubed. So the good news is that this aberration cancelled out. It disappeared from the result. Now, is this clear to everybody? Okay, I didn't dwell on it when I talked about differential sensors, but since I mentioned it now, I may as well show you the proof. So basically what this shows, that all the even distortion components cancel out in a truly differential sensor. So in other words, if there was an x squared and x to the power of 4, if the sensor was truly differential, they'll cancel out, so you'll get better linearity. So a nice bonus on truly differential sensors is slightly improved linearity. It's not a very big factor. Most of these sensors are linear enough. And as I said today, if you really want perfect linearity, you can use a lookup table and linearize them. So today the stability is much more important than linearity. Okay, so summary of all that. You're trying to work at low impedances, you're trying to work truly differential, which has a long list of advantages. If you can't work truly differential, you're trying at least to put in a dummy sensor to compensate against aging, temperature changes, and so on. This dummy sensor idea is especially important when you are making measurement on some complex sensors, which chemical sensors, for example, which have a lot of aging problems and changes. When you look at a resistor, it's not so important if you have a dummy sensor or not, because everything which happens to it is predicted. Some people actually put a temperature gauge too, and then they can compensate the results for temperature by reading. But when you are dealing with a complicated sensor, like most of the time chemical sensors, like gas sensors which sense toxic gases in air, these sensors are very strange. They are chemicals, they change with time, change with temperature, change with everything. So it's much more important to put in a dummy sensor. Okay, where another case where a dummy sensor is put in, let's say you want to detect a presence you want to detect optically the presence of a very low amount of gas in air. Let's say you're looking for helium or argon in air. You want to detect it optically, but air has many other gases which change a lot more than the gas you want to measure. So this is a place where you actually almost cannot do it without a dummy sensor, because the quantity you're measuring is buried in quantities which overshadow it. So what you would do is you would take two tubes with air. One will be sealed, the ends will be sealed, and you shine a light through it. The other one will be open, so the air can flow through it, and then you put two detectors and you take the difference. So basically this is reference air. Air, you know the composition. This is the room air which flows through it, and you're only measuring the difference between this air and the reference air. Because if you try to directly measure the air, the thing you're trying to measure will be overshadowed by huge variations in the optical properties of air. Right? Do you understand? So basically the trickier the measurement is, or the trickier the sensor is, or the worse the signal to noise is, the more important to use something differential. And if you can't do a differential, it is use a dummy sensor. Okay. So this summarizes the first part of sensors, and what I want to move on today is to optical sensors. Now the reason I want to spend a lot of time on optical sensors, because if you want to draw a curve or a prediction into the future, where will most sensors in the future be? So if you looked 50 years ago, there weren't that many optical sensors. The most popular sensor was LVDT, there were some other electromechanical sensors, there were very few optical sensors. If you look today, there is a lot of optical sensors. Things which used to be done electromechanically or magnetically, today a lot are done optically. So can somebody guess, there were two major inventions which shifted the use towards optical sensors, and since you are training here not for something which is happening today, but you are training here for things you'll have to use, let's say, in the next 20 years. So it's better to think a little bit, where will sensors be in 10 years from now? Okay? And if you think about it, you realize right away that there will be a lot more optical sensors. Almost everything will be sensed optically 20 years from now, so it's better to understand optical sensors well, because that's the type of sensor you're more likely to use 10 years from now. So first the question, why is the popularity of optical sensors going up and up? From basically, I can even say more than that. I can say if you draw a graph, okay, if you draw a graph and this is year, and this is say 1900, and this is 2000, okay, and we are here, and this is the popularity of optical sensors. You see something like this. There was none used in 1900, and then it started going up a bit, like this, and then it went up a little bit, and then in somewhere here, in let's say 80, it went up and up and up, and now it's going like this, and the year 2000 it went up and up like this. So what happened here, what happened here, and what happened here, just to give you a hint, why the popularity of optical sensors went up and up and up around these points. This is more around this, 1980 here. This is 1980. So think about it. The graph looks something like this, so something very important must have happened around 1900, around 1980, and around 2000, which made the popularity. And if you predict into the future, certainly it looks that optical sensors are going to go faster and are going to be the most popular sensor. So, yeah.
The digital camera, like digital.
Okay. Because first of all, digital. That's a very good answer. Which point is this of the three?
The
Yeah, correct. Okay, what happened here is something very important. A CCD camera price point reached $1. Okay, now you may not know that, but the cameras in your cell phone, which are excellent cameras, multi-megapixel, they cost the cell phone vendor $1. And this is a camera with a lens and electronics and everything, processing. So that's amazing. It's amazing you can buy a camera with processing and everything with megapixels $1. This is at $1 million quantity. But you know, even at smaller quantity, it couldn't be much more. For example, a webcam that you buy for a computer, you can buy a webcam for $10. If you buy it from China, it's $2. Quantity 1. If you go on eBay, look for webcam for $2, you can buy a webcam at quantity 1. That's $2. It uses the same cell phone technology inside. Okay. And you can actually buy little cameras which are cell phone cameras for $3. But in volume, it's one. So something amazing happened here. The volume of camera chips made went up 100-fold because every cell phone has a camera, but that's not the main reason, because everybody replaces the cell phones all the time. In the old days, people also owned a digital camera, but you kept it 10 years. Today you have a cell phone, but you replace it every year. Half the time because you break it or lose it, half the time because it's obsolete. Okay? So suddenly, even if the number of cameras was the same as the number of cell phones, you have 10 times as many cell phones made every year. Okay, and actually there's a lot more cell phones and users than camera users. So one thing happened here, and this is the $1 CCD camera. So now it suddenly becomes cheaper to use a CCD camera for very, very simple jobs. I talked a lot about measuring displacement. Why do you need any measurement? Why not put a CCD camera, look at the thing, and then use some simple algorithm to calculate how much it moved? So why do you need a sensor at all? If you can buy a CCD camera for $1, and I want to measure the displacement, let's say, of this piece, I just look at it. I count how many pixels are on, how many see white, how many see black, and I just add up the pixels. So I don't need any sensor. Because an LVDT you cannot buy for $1 no matter what the volume is. Okay, so the first thing which happens, a $1 CCD camera appeared on the market. So then each time you need a sensor, you're saying, why do I need a sensor at all? Why don't I look at it? I have a computer anyway, because most systems have a computer. All I have to do is add $1, I can look at it. And if I want to measure acceleration, I can make a cantilever and a mass and just look at it and calculate the deflection. If I want to measure whatever I want to measure, you know, if I want to measure pH, I can use something which changes color and look at it. Okay, so this changes the thinking completely. Okay, so that was a good answer. Year 2000, they're cheap, very good cameras. By the way, do you know how big is the camera on a new cell phone? Kind of in terms of millimeters. How big is the module, the camera and the lens and everything? You can look at it, yeah, but what you see is the lens, but the thing behind it is no bigger than the lens. So in new cell phones, the camera module is about 5 millimeter by 5 by 5 millimeter. You can buy them today down to 2 millimeter by 2 by 2. Like a cube, 2 by 2 by 2 millimeters. That's a whole camera with a lens and processing and everything. So it's also probably smaller than anything else except capacitive sensors, which are micro-machined. So it's the cheapest sensor, the smallest sensor, and you already have a computer. The computer already has an interface for it. Okay, so why not use it? So this is first point. What happened in 1980? Something even more important.
Processing capacity?
Pardon?
Processing capacity?
Yes, but even non-computer sensors, because this camera needs a computer, but there's optical sensors which don't need a computer, and something happened in 1980 which made them vastly more attractive. Things like encoders, anything which, even without a computer, which becomes optical. Like, for example, before 1980 there was a lot of magnetic encoders. Okay, let somebody else answer maybe. Yes? CDs, indirectly yes, but you can say what enables a CD? It's the same thing, yes?
Lasers get cheaper?
Pardon?
Did lasers get cheaper?
Not just get cheaper, laser diodes became available. Because and another thing became available, LEDs. Because here, in this period here, the only light source which was small enough to put in a sensor was a light bulb. Now the light bulbs, you have two choices. Either you run them very dim, so they don't burn out and you have very little light, or you run them bright, you have a good signal but they burn out. Now that's a big problem. If you have a sensor inside some inaccessible place, the light bulb burns out. So in this period, most of the effort was to design sensors that somehow either the light bulbs don't burn out or it's easy to replace the light bulb. So some clever ways you can plug in light bulbs and so on, but they burned out. Now, laser was invented here actually. What year was the laser invented? 1960. Actually, the fellow who invented the laser, Ted Mayman, lived in Vancouver the last 10 years of his life. So there's a connection to Vancouver. So this is laser, but these were big lasers. But 1980, around here, 1970, laser diodes were invented. When 1980 they became popular. So this point is laser diode became popular, and LED, because LED started a bit earlier, but sometimes you need much more intense light. So in 1980, suddenly you could get very cheap laser diode. So this enables a CD, as somebody here said, so it is connected to the CD, because the same technology enables a CD player, but it was a blessing for people who make sensors, because the laser diode is very bright, can be focused to a very small spot if you need high resolution, can have a huge power. So basically it's an ideal light source. It's also monochromatic, meaning one frequency, one color, which makes the optical design much easier. Because when you design an optical system for white light, you have to color correct, you have to have multi-element lenses. If you have a laser diode or even an LED, it's only one color, it's much simpler. So this is the second breakthrough. So what happened here? Or why were there no optical sensors before 1900? Pardon? No.
Light bulbs.
Light bulb, who said that? Yeah, light bulbs, very simple. If there's no light bulb, you can't make an optical sensor. I mean, some people made some sensors with candles to detect vibration, but these were lab sensors. There were setups in the lab with some candle, but it wasn't a practical sensor you can build it or something. You couldn't put some, anti-ABS system with candles in the car. So basically, you needed a light bulb. So the first optical sensor couldn't come before 1900. Okay, light bulb was invented a few years earlier, but it was unreliable. 1900, light bulb was reliable enough to put in. So these are the three break points. So this is a light bulb, the tungsten light bulb, I should say, because, as I said, light bulbs were available before, but they were carbon filament, and they were brittle. Here, tungsten came along. So there were 3 points in the history of optical sensors. Each one increased the use 1,000-fold. Okay, so light bulbs, and LED and laser, and then CCD and computing power. Okay, so that's a short history of optical sensors. So now, today, where we are now, I would say maybe 70% of the sensors in new designs are already optical. And probably by the time you'll be in mid-career, maybe 90% of the sensors in new designs will be optical. Okay, so that's very good. There is one little catch in that it turns out students, even grad school students, don't understand optics. Okay, so I have to devote the rest of the lecture today to do an optics refresher course, because without that we wouldn't be able to discuss optical sensors. By the way, one nice thing about CCDs, I mentioned CCD cameras as sensors. When you have a CCD camera as a sensor, it's automatically XY sensor. Right? Because when I talk about LVDT and so on, it's single axis sensor. When you have a camera, you get for free a 2-axis sensor. So if you have 2 cameras, you get a 3-axis sensor. Okay, and there's actually tricks to even get with one camera 3 axis. So basically, you get the second axis for free, which is nice, especially in robotic applications, things like this, where it's all 3D. Okay, so quick refresher of optics. First thing is, when light hits a surface, it can be reflected or come back in 3 different ways. So there are 3 types of surfaces. If this is the surface, I'll draw the 3. And this is the light hitting it. One surface is a simple mirror, okay? The scientific word for it is specular refraction. Okay, but it's just a fancy word for mirror. So when light hits a mirror, it will just come back like this. This angle equals this angle. Very easy to demo, so all of you know that. Okay, okay. So this is one of these amazing things that these are the green laser pointers that people don't even realize how amazing they are, because that's a frequency doubled laser inside. So it's a frequency doubled. It's quite an amazing technology. But anyway, when I take a mirror, I hit the mirror, the light will just be deflected by the mirror, and all of you know that. So that's the first type of reflection. The second type of reflection is a diffusing surface. Okay, and this happens when light hits, say, a white surface. So if I take the other side of the mirror, I have a white surface. When light hits this, watch what happens. You saw what happens with the mirror. Now when light hits this, I'm getting some reflection, but it's very blurred. Okay, so the mirror gave me a sharp spot. This gives me some blurred spot. Now, and I can see that if I take different materials, I get different amount of blurring. Let's say if I take this paper back here, I'll get a more blurred reflection. If I take pure paper, not coated or anything, I'll get an even more blurred reflection. May I borrow this for a sec? Just the paper, yeah. So if I take pure paper, I get a very blurred reflection. You can see the whole thing lights up in green. It's completely blurred. Okay? So this is called diffuse reflection, and the light comes back in a general direction like this, but it comes back like this, diffused. Now, the more textured or micro-textured the surface is, the more diffuse it will come. So this will be like gloss paint, and this will be like matte paint. Okay? And this will be like paper. Okay? So in theory, if something is a perfect diffuser is defined that if a beam hits it, the light will come back over a full 180 degrees. That's a perfect diffuser, but it wouldn't come back at the same intensity. A perfect diffuser, the return light looks like this, where the intensity here is bigger, intensity here is smaller. Okay? But it comes back all the way to horizontal at a smaller intensity, and there is some cosine law for the intensity, but that's less important for you. So this is a perfect diffuser. Most real-life diffusers look like this. Okay? The third type of reflection is called a retroreflection. And this is if the light hits a material and it comes back exactly in the same direction regardless of this angle. Even if you change this angle, the light will always come back where it came from. How many of you own a retroreflector? Okay, who here doesn't own a retroreflector? Okay, so I guess you don't care. So, okay. Anyway, anybody who has these reflective strips when you bike or jog, these are retroreflectors. Okay, so what they do, they send the light back exactly where it came from, regardless of direction. And that's why they work so well. When you have headlights in a car and the headlights reach you, the light will come back to the driver regardless of the direction. So this is a retroreflector of the type you see on traffic signs, bumpers on gear for biking. Now this is a very good one, so it's a bit hard to demonstrate because on this one the light comes back exactly into the same hole of the laser where it came out, because it's a very high grade one. But what I can do is I can put it here, and if I go at a big distance, of course it spreads somewhat, so the bigger the distance, the more I'll be able to see that the light is coming back but misses the hole somewhat. So if I hit the wall, this tip of the laser is dark because no light is coming back here. I'll do it like this so the camera can pick it up. So if I hit this wall, okay, the tip of the laser stays dark because no light comes back, or the little which comes back is so weak, it's very weak. Okay? Now watch this paper when I'll hit the retroreflector. See, the moment I hit the retroreflector at the bottom, see, suddenly the paper lights up. Look at the paper and look at the wall. The moment I hit the retroreflector, the paper lit up. Did everybody see that? You didn't see it, so I'll do it from this side so people here can see it. So if you look at the paper, when I hit the wall, paper stays unlit. But the moment I hit the retroreflector, the paper lights up. Okay? So this is quite an amazing device because the light reflected from the wall here is probably 100 million times weaker than the light when it hits this. Okay? Because this light, even in a dark room, I wouldn't be able to see the light hitting the wall. So if I hit the wall, I just want to be careful not to hit people. So even in a dark room, I can't see on the paper the light from the wall, but watch when I hit the retroreflector. See how much light comes back. Okay? So since the eye responds to the log, the eye's response is logarithmic, when you see something like 100 times brighter, it actually means it's like millions of times brighter. Because a lot of human senses are logarithmic, so they can cover a very wide range. So, for example, actually I would say all human senses are logarithmic, because the human ear covers 140 dB, right? So it's 10 to the power of 14. Okay? The eye covers something comparable, at least 10 to the power of 10. Okay? Because a human eye can pick up from nanowatts per square centimeter to watts per square centimeter, probably more than that. Above that it blinds you, and below that you have to be dark adapted for a very long time. But certainly a human eye will cover 10 to the 10, the ear will cover 10 to the 14. Okay, but because it's logarithmic, it doesn't look to you like 1,000,000 to 1 different. It looks to you maybe 1,000 to 1. Okay, so these are the three types of light reflections, and each one has different uses, of course. For example, if you want to measure the angle something moves, you would use a mirror, not a retroreflector. Because a retroreflector, when you tilt it, nothing will change by definition. Okay, on the other hand, if you want to make a garage door opener where it's inhibited by you walking across the beam, so you want to put if you wanted to make a safety device in your garage, so if your car is under the door or you're under the door, it doesn't close. So this is your garage. Okay? Typically what you want to do is put some source here which shines a beam. Okay? So if something is here, the garage door doesn't come down on you. So the one way to do is put a laser pointer here and put a detector here. But this has two problems. Problem number one, you have to run wires to both sides of the garage. Problem number two, it's very sensitive to alignment. If the laser pointer is just tilted a little bit, it will miss the sensor. So for an application like this, you're much better off to put a laser pointer here with a sensor next to it and put a retro reflector here. Because then, regardless of alignment, the light will always come back even if it's misaligned. Okay? So that's a very good example where using a retro reflector, yes please?
Do those retro reflectors, do they only reflect certain wavelengths? Of
No, I'll explain how they work in a sec. They reflect all wavelengths the same, or almost the same. But you can make one which reflects all wavelengths the same. So this, for example, this is an example where a retro reflector is the right thing to use because it's completely alignment free and allows you to run wires only to one side. Okay? So that's a very good example. Not the way they did it in my garage, because in my garage they put the beam 10 centimeters above the ground, so of course when the car is here, it goes under the car and the door can close. but I hope your garage is better made. But anyway, okay. Understood? Good. Okay. Now let's explain. Okay, so how this works is clear, how this works is clear. This diffuses because this is microscopically bumpy. So because it's microscopically bumpy, each bump returns the light in a different direction. Now, how does this work? Okay, so the way this works is typically by what's called a corner cube prism. Okay, so to understand the corner cube prism, let's first draw two mirrors at an angle of 90 degrees. So this is the right angle. Now, when a ray of light comes in here, it gets reflected to here, and then gets reflected to here, and comes back in the same direction if this is 90 degrees. Now, it's very easy to prove that, because it's a simple geometric proof, because because basically these two lines are also perpendicular, because these two lines are perpendicular to the mirrors. Let's draw the mirrors. These are the mirrors. Now these are the vertices to the mirrors, or vertical lines. Now this angle is the same as this angle. Okay? So just from simple geometry, regardless of the angle, okay, this angle plus this angle will always be 90 degrees, or this angle plus this angle will always be 90 degrees, because this is a right angle triangle. If one angle is 90 degrees, the sum of the other two angles is also 90. So this equals this equals this. Sum of these two is 90, so the sum of these four has always to be 180. Is that clear to everybody? Great. Okay? So basically, if this is alpha, beta, if alpha plus beta has to be 90, then this is 2 alpha plus 2 beta is 180, so the light will always come back straight. Now, what is interesting, that this is also true if you take 3 mirrors and you make a cube. So if you take 2 mirrors, like this, you have a corner cube. But if you add a third mirror, what's interesting that if you shine a light into that corner, it will bounce in 3D, but the sum of the angles will also be 180 degrees. That's an excellent exercise to think out in your mind if you have problems falling asleep. Okay, why is also true with a cube, with a corner, not just with 2D. Okay, good. So that's how these things work. So when you make the highest grade retroreflectors, all what they are is many little cubes like that spread on a sheet. They don't have to be aligned, because one of the qualities of a retroreflector, if I rotate it, it will work the same. Okay? So because of that, when you spread those on a sheet, you don't have to align them carefully. So the highest grade retroreflectors are simply a sheet covered by little things like this. And this could be actually metallized, could be plastic and metallized. So any ray which comes in will be retroreflected. Okay? You can also do it with a solid prism based on total internal reflection, because it turns out when you take a piece of glass and has a high enough index, when the light comes in, the light will bend or refract, but it wouldn't come through the wall. It will actually hit again like this, and if the angles are right, okay, it will reflect like this and come back straight like this. So this is called TIR, total internal reflection. So you can do this with a piece of plastic which has a shape and you metallize it to be a reflector, or you can do this by actually taking little prisms made of glass and sticking them together, and the light will be trapped inside and returned by TIR. I wouldn't get into that, that's not important. Okay, now, so these are the high grade retroreflectors. You can buy those things for very precise measurements where it's guaranteed that the beam will come back to within 1 arc second. Now 1 arc second is very, very small amount. 1 arc second is 5 microradians. Okay? So 5 microradians means if I shine a beam a kilometer away, if I used one of those 1 arc second retroreflectors and I shone this laser pointer a kilometer away, the beam will still come back into the hole. Okay, because that's 5 microradians on a kilometer. 5 microradians is 5 millimeter, so it will still come back into the hole, almost. Okay, that's 3 millimeter hole. So that's quite amazing. I think you can buy them. The best in the world you can buy is even 0.1 arc second. And those will be quite amazing. It'll come back after a kilometer, less than a millimeter off. But the usual ones are not as good, of course. This one we saw that over this distance, maybe it was 5 centimeters away. Okay, so we can calculate what it is in terms of. Now, but there is one version which is easier to make and is cheaper, and that's the one that you have on all your bike gear and so on. And this takes advantage of the fact that if you have a sphere of glass, it behaves like this. And that's just coincidence, by pure luck, because of the refractive index of glass. Now, is there anybody here who doesn't know what refractive index means? Good. Okay, so when you take a sphere of glass, it acts as a lens. Okay. Take a sphere of glass, it acts as a lens. So when light comes in here, it gets focused. And as luck has it, for normal glass, where the index is about 1.5, it ends up being focused right on this wall. And since every material has some surface reflection, even if it's transparent, some light is reflected from the surface, the light comes back, it goes in this way, comes back this way, and retro-reflects. So any sphere of glass, regardless of size, retro-reflects. And sometimes people refer to these things as cat's eye reflector, because when you see a cat in the headlight, or any animal in the headlight of a car, the eyes shine very bright. The reason the eyes shine very bright is because of this. Because every sphere with the index close to this number acts as a retroreflector. For those who really have to see the proof, there is a formula for the power of a lens. And the formula says 1 over f equals 1 over r. Equals, let me just get it right, 1 over f equals n, 1 over r1 minus 1 over r2, where this is the radiuses of the lens. If you have a lens, let's call this r1, let's call this r2, This is called the lens maker's formula, but let me just check if I got it right, if it's n or 1 over n. So let me just check. And yeah, that's correct. Okay, so here this is R. So 1 over R1, 1 over R1 and 1 over R2 is the same, except one is negative, because you measure the radius positive this way and negative this way. So this will be 2 over R. Okay? So 1 over F is going to be 2n over R. Oh, sorry, it's n minus 1. Okay? I'm trying to build up the formula from memory, so give me a few seconds to reconstruct the formula, because there may be a factor 2 somewhere here, but yeah, okay. No, okay, the formula is correct, but what I'm not interested in this side at all. I'm interested where will this light hit. So this is a formula to calculate it. So now let's plug in the numbers. 1 over F equals n minus 1, which is 1.5 minus 1, because n is 1.5, times 1 over R, because I'm not interested in this wall, I'm only interested in this part where it will focus the light. So 1 over F will be half over R, will be 1 over 2R. So what you get if you plug in the numbers into the lens maker's formula, you get that 1 over F is 1 over 2R, which gives you F equals 2R. So what it tells you that if you hit a glass surface with light and the surface has a radius R, the focal length will be twice that, 2R. But 2R in a sphere is exactly the other surface, right? Because 2R is the other surface, it will hit this other surface and reflect back. So it will hit a point here, reflect back, and come back parallel again. So that's why the eyes of animals light up in the headlights. Okay? Now, why does some light reflect when it hits a transparent medium? Even if the medium is transparent, when the light hits it, some is reflected. So that goes back to wave theory, because there's a change of velocity of propagation, so some of the light is reflected. That's the same as in electromagnetic waves. You can calculate that. The amount of light reflected is, again, that's Fresnel's formula. It's n minus 1 over n plus 1 squared. So if you plug in this number, it will be 0.5 divided by 2.5 squared. Okay, so this is 1 over 5 squared will be 1 over 25. 1 over 25 will be 4%. Okay, you don't really have to know all that, but you can actually calculate how much light will be reflected when it goes from one end to another end. Okay, and here it goes from n 1.5 to air. Okay, so I plug in, that's the formula, 1.5 minus 1 is air. N plus 1, I plug in the numbers, I get 4%. So 4% of this light will be reflected. But if I silver the back, 100% of the light will be reflected. So the other way to make very cheap and good retroreflectors is take some silvery material and just coat it, or say take some even white material and embed in it glass spheres. So any light hitting the glass sphere will be hitting the silvery background and retroreflect. Okay? But this doesn't work as well as the one with a mirror. And let's see if somebody here has some understanding of optics. I'm saying the cheap ones are made like this, the good ones are made like this, because the idea with a sphere doesn't work as well as the idea with the mirrors. Can somebody think why? Yes? Not quite, because both can be polished perfect. The sphere can be perfect. It's fundamental. The reason I'm mentioning this because that principle applies to all optics. Yes?
Gaps between the spheres?
Pardon?
Gaps between the spheres? Spheres that's...
Yeah, that is a good point, but you can pack the spheres touching, so then there's practically no gap. But the answer is very different. The answer is that n is not fixed. The index of refraction is a function of wavelengths. Because any material has a property called dispersion. If you remember this experiment with a prism. When you take a prism and you put in white light, it separates to different colors depending on the wavelengths. So this will only be true for one color where the index is exactly 1.5. So if you shine white light, only one color will come back stronger than others, while a mirror reflects all wavelengths the same. So the lesson here is that a reflective optical system, if you can build it, is usually better than a refractive. That's called a refractive system, that's a reflective, because any refractive system will, unless it's color corrected, will suffer from wavelength aberrations. You change the wavelength, it works different. While a reflective system works exactly the same because it's purely geometric, works exactly the same for every wavelength, and this explanation is true for all optics. However, today with lasers it's less important, because if you're going to use this for optical sensing, you can just pick the LED or laser where this is exactly correct. So, but white light, it is important. Yes, please.
So why you get red eye in photos?
Yes, because that's exactly the reason, you know, the red eye in photos, because your eyes, it's actually a little bit more complicated. The eye is a retroreflector, but in the eye at this point there is something red. And what is it? What's in your eye at this point? Retina. And what does the retina have? Lots of blood vessels. So in a retroreflector you put some white background to get white or silver. In a human eye, where it hits is where all the blood vessels are, so what you get back is red. But that's exactly the explanation why it comes out so strong, because when I look into your eyes I don't see red, because very little light comes back from inside the eye. The inside of the eye looks black. When you look into the pupil of a person, it looks black because light goes in, very little comes back. But because it's a retroreflector, when you take a picture with a flash, all the light which enters the eye comes back and carries the color of the blood vessels, and that's a red eye. Okay, so we have to move on. So this was the different types of reflections and the lens formula, and now there's one other thing I have to explain in optics is how a lens works, and then we'll be done. So all of you know that a prism bends the light, because you know that if you have a prism, if light hits it, it will be refracted, it will be bent, and when it hits this point it will be refracted again. So the prism bends the light. You also know that if the light is shorter wavelengths, it will bend more. So this is lambda 1, this is lambda 2. So lambda 2 is less than lambda 1. Okay? And now, who is the first one who formulated this? Because there is a formula which tells you if this is alpha and this is beta. There's a formula which gives you the beta as a function of alpha and the index of refraction. And who formulated this? Snell, of course. That's Snell's law. And Snell's law says that the ratio of the sines of the angles is the same as the index. Okay? So basically sine alpha divided by sine beta, that's the index. That's Snell's law. Okay? So, the best way to explain how a lens works, saying a lens is simply a superposition of a bunch of prisms. Let's take one prism, another prism, another prism, and do the same on this side. I mean, that's just one of many explanations. I find this is the fastest. So what happens when you get parallel light hitting the lens? these two prisms will bend it to this point, these prisms will bend it a bit more, and these prisms, because are steeper, will bend it even more, so all the light will hit one spot. Okay? So that's kind of a very simple explanation what a lens does. So if I replace this by two radiuses, and I have parallel light, each one will be bent a bit and bent again, and they all come to this point, and this distance is called focal length. Okay? And it's easy to demonstrate. I can take a lens here. This is magnetic. Let's see. Yeah, great. Okay, so I can shine parallel light. So parallel light here stays parallel, but if I go through the lens, and I can use, if I go through the lens, it will bend. Let's see, like this. Watch where the light is going. When I go through the lens, it bends. So there is a point which I can go. There is a point where all the parallel rays will cross. So watch. So if I mark this point, all the parallel rays will cross it. Just go a bit shallower so you can see the ray. It's not so simple for me. I could see it better before, but anyway, like this. And if I go like this, no matter one point, no matter how I move the parallel light, the rays always cross this point. So what you saw when I came in with parallel rays, they all cross this point. Okay? That's how a lens works. Now, what is important to understand about a lens, that if I have a single ray of light and I move it, if I am located at the focus, nothing will change. So for example, if I put the chalk, or let's see if I can put something, I want to put something you can see the light. So if I am located here or here and I move the parallel light, everything will move. Okay, this is my lens. If I'm located here and I move the parallel light, I can see it moving. It's moving opposite to this direction. Here it's moving like this. But after a lens, it's moving in opposite direction, but it's moving. It's moving in opposite direction because it's crossing the focus. Now, if I am at focus, exactly at focus, when I move this, nothing will happen. See, right now I can move this light and nothing happens. So that's the definition of focus. I'll put it higher so everybody can see it. So if I'm located at focus, moving the light in parallel doesn't do anything. I have to find the focus. It's exactly the focus. If I go away from the focus, it will move. If I'm closer than the focus, it will move. If I'm exactly at focus, nothing will happen. Okay? Now this is very important to understand for sensing. On the other hand, if I tilt the light, it will change. So if I am at focus, this is focus, parallel motion does nothing, tilting moves it. Right here, the parallel motion again wouldn't do much if I was at focus, but the fact I tilted the beam will move it one to one. So the lens acts as a pivot. The lens acts as a pivot. If I tilt the beam, the focus will tilt, but if I move the beam parallel, the focus will stay. Okay? That's very important. You'll see next week why is that so important, because that is the basis of designing optical sensors. Okay, so when I draw a lens, so if I have a beam coming in here, which is coming to a focus, this is a focus. Say if I block half of the beam, nothing will change. I will just get less light. Okay? Or if I have a pointer and I'll move the pointer like this, nothing will change, all the light will come to focus. Okay? Now if I tilt it, it will act as if it's pivoting around this point. It'll come to focus here, and if I tilt it, if I had a lens here, it'll act as if this was a pivot point. Okay? So what this means that if I want to make an optical position sensor, I say I want to make a sensor which measures lateral position. And if I put a lens here and I put a sensor here, it wouldn't work, because I can move it laterally, but if there is a lens here and that's focus, it wouldn't work. Okay, so this arrangement is good for measuring angular position. Okay, if I wanted to measure lateral position, I would need to do something different. But so you can take advantage of these properties of the lens to eliminate what you don't want. For example, if I want to make an angular position sensor, this is very good, because if I put a detector here, angular position will be measured, lateral position will make no difference. So this is exactly what I want, because a true angular sensor should ignore lateral position, right? Because if I want to measure how horizontal this is, ideally I want a sensor that will measure how horizontal it is, but would not be affected by this. Without a lens I cannot do that, because without a lens, looking at the wall far away, I cannot tell this motion apart from this motion. But with a lens, this motion will give me one-to-one motion, this motion will do nothing. Is that clear to everybody? Good. Okay, so the lens gives me, although it's a very simple element, gives me all kinds of interesting possibilities to separate the desired quantity from the undesired quantity. So, if I wanted to make an angular sensor which is immune to rotation, immune to shift this way, immune to shift this way, only responds to angle, I would take a lens, put the detector at the focus. Now what if I want the opposite? What if I want a detector which is completely immune to this but only measures lateral position? What would I do? That's trickier. Pardon? Move the lens. Good. If it was a wide beam, yes, if I had a wide beam and I can move the lens in a wide beam, and this will be my sensor. That's a good answer, but there's even a simpler answer. Okay, if I reverse it, okay, if I put the light source here, okay, and I work the other way, now it wouldn't depend which angle I am, because all angles will come back parallel. Okay, it wouldn't depend on the angle at all. But if I shift it, if the light comes out here at a wide angle, say if I have an LED, not a parallel beam, and I shift the LED, say if I shift the LED from here, the light will come out this way and shift. So if I put a detector far away, okay, and I put an LED at the focal point, parallel shift will change the angle, angular shift will do nothing. So I'll show this one more time to be more clear. If I take a source which already shines in all directions, if I take an LED, it already shines in all directions, and I put it at focus. So the central ray connects the LED to the center of the lens. This is the central ray. The other rays will come out parallel, because that's what a lens does. If I tilt the LED, it makes no difference, because it already has light in all possible angles, even angles which miss the lens. So tilting it makes no difference. Okay, but if I shift it, if I shift the LED, the central ray, which connects the center of the LED to the center of the lens, is going to be tilted, so all other rays are going to end up parallel to the central ray. Okay, and I can show it to you. I'm taking this lens, and now what I'm doing, I'll shine a light. Okay, I'll shine it so you can see it on that wall. Okay, and I put it in focus. Now when I move up and down, I get a very sensitive detector, because I'm moving it a centimeter and I'm moving there a meter. Okay, but if I'm tilting it, if I was exactly, well, I'm not exactly in focus, but you can see the pointer is tilted a lot, and if I was exactly at focus, the light wouldn't change at all. So watch the spot. If I tilt it, well, I'm also moving it, but if I tilted it, nothing will change. But if I move it, I get a huge movement. So if I put the LED at the focus, I'm getting a detector which is only sensitive to position, to displacement. If I go the other way, if I put the sensor at focus, I'm getting a detector which is only sensitive to tilt but not to displacement. Is that clear? Okay, so this was just an example, the clever things you can do in optical sensors just with an LED and a lens. I did the demo with a laser diode, with a laser pointer, because that's much more visible, but in real life you don't need a laser. All these things that I talked about you can do with an LED, which is much cheaper and simpler. Okay, so I think that's about the basics of optics you need to know. There is one other thing you need to know in optics, and that's imaging. When you have a lens and you put an object here, at some distance an image will appear, okay, like in your camera or in your eye, okay? And if this distance is u, and if this distance is v, and this is the object, let's say object, and this is the image. There is a formula that I think you learned already in high school, that 1 over u plus 1 over v equals 1 over f. And this is the most basic formula there is in lenses, okay? So now it allows me to calculate if it's not just a collimated beam. If it's a collimated beam, it comes to focus at f. There's nothing to calculate. But if it's not a collimated beam, if it's a beam like this, which is coming to a focus like this, and this could be a point, like an LED coming to an image of an LED, or could be a whole scene. A whole scene will be like this, and let's say people usually draw a tree, and this will come to an image here. It will just look inverted, just like in your eye or in your camera. And this line will be this line. So basically all the lines which goes to the center of the lens don't get modified. Okay? So if you want to calculate, if this is a distance u, and you want to calculate where the image will be, then 1 over u plus 1 over v is 1 over f. And there is one other thing about lenses, which I'll have to carry over next week to explain, is this number, or that angle of the rays, affects a lot the imaging performance. Now, you are used to cameras. In the old days when you had cameras, on the lens there was some adjustment, and it says f8, f11, f4, and that's the f number. You know what I'm talking about in cameras? Good. Okay. So the f number is the ratio of this diameter, which was set in a camera by an iris. Same as in a human eye. In the camera of an iris, it sets this diameter, d, to this distance, which was usually referred to the focal length, because the camera lens was calibrated with parallel light. So this distance was f. But if it's not parallel, we still call it f in a camera. So this d over f, that's called the f number of a camera. Okay, so if the lens says f11, it means this distance is 11 times this. Okay? And it seemed to be a very important number, because all cameras had it calibrated and optical instruments had it calibrated. So the question is, what does this number determine? When I change the f number, what changes? Because the image doesn't change. The image stays at the same place, because the image is bound by this formula. So if instead of taking all these rays, I'm taking some of these rays, the image doesn't change. But what changes? Amount of light, first of all, because of course if I cut down some of the rays, I have less light, and that's very important. It changes like the square, actually, of the f number, but something else changes, which is just as important. depth of field. Depth of field meaning at what range will I get a sharp image. So anyway, we'll continue that on Tuesday because we ran out of time. If you're really bored, you can look up optics in Wikipedia and just go over it a little bit so you're somewhat prepared for next week. Thank you. Okay, so what a lens does, that any parallel ray entering the lens, and the way I show parallel rays, I move the laser pointer sideways. All the parallel rays will hit one spot called the focal spot, and you can see the path. You can see the parallel ray hitting the lens and continuing to here. All the parallel rays will hit the spot, which means if I move the laser pointer side to side, this spot will not move, assuming it's exactly at the focal length. If it moves a bit, you can adjust it until you find a point where it's exactly at the focal length, and then it doesn't move. On the other hand, if I tilt the laser, it will move. So you can see if I tilt the laser, it moves 1 to 1. And you can also see that if the ray goes through the center of the lens, this acts as a pivot point. If I send, so this ray will go through the center. The other rays, which are parallel, will reach the same point. So again, if you are looking at the focal point, it's immune to parallel shift. It only sees angular shift. Okay? And this also allows you to do the opposite. If you want something which only responds to parallel shift, you do it the other way. What you can do is you put this at the focal point of the lens, and then you look far away. So now, because all the parallel rays will cross this point, you'll get a movement with parallel shift. Now at this point, at the focal point, you get no movement. But farther away, you'll get a movement from parallel shift. Okay?